Hello, everybody. I'll give people another couple of minutes as folks try to connect into our webinar. So we'll start a little bit slowly. But I wanted to welcome you to the webinar series on PaxCon Reflections. My name is Cindy Palinkis, and I am an associate professor at the University of Maryland Center for Environmental Science, Horn Point Lab. And I am delighted to be the moderator for today's panel. So just a couple of notes. First, please be sure you're muted. We have a photo of what the mute button looks like. Also, I would like to remind everybody that this is being recorded. So if that is not okay with you, I invite you to leave now because we are recording. If you turn off your video, you can change your name if you want to, but just be aware that we are recording today's session. We'll be doing a Q&A after our two presenters. And the way we will do that is we will use the chat box. And so the instructions are at the bottom of this screen. Just click on the button that says chat and just type your question right in there. Sorry, wrong button. So if you want to see the other webinars in this series, we invite you to go to the website, www.paxcon.org. And there you will see the other sessions that I'll get to in a minute. But first, we would like to acknowledge and thank our supporters that are listed on this slide here. And here are our next sessions. We have one on November 5th on the importance of wetlands in the region. And we have one on the 12th on stream ecology and restoration. And we have one on the 19th for outreach and advocacy for river health. So today we are talking about climate change and the Patuxent. And unfortunately, I forgot that I need to move my computer to see the bios for our two speakers today. Apologies for that awkwardness and the view that you're now getting of my face. But first we will have Dr. Kate McClure. Kate is a coastal climate specialist with the University of Maryland Sea Grant Extension Program. She is based at the Y Research and Education Center in Queenstown, Maryland, and serves coastal communities throughout the state. Kate works to assist residents and decision makers with understanding and preparing for the effects of climate change, with a focus on flooding due to sea level rise, precipitation, and storm events. Her background also includes experience in informal science education, science policy, and marine ecology research. Kate holds a PhD in evolution, ecology, and marine biology from Northeastern University and a BS from the College of William & Mary. So Kate will be speaking with us first, and then we will have Jeremy Testa speak with us. Dr. Jeremy Testa is an associate professor at the University of Maryland Center for Environmental Science, Chesapeake Biological Laboratory. His interests reside within the field of coastal marine ecology with an emphasis on the processes of eutrophication, nutrient cycling, and dissolved oxygen dynamics. His group is especially interested in the interactions between biological, chemical, and physical processes in coastal ecosystems. They use a combination of experimental efforts, historical data analysis, and coupled biogeochemical hydrodynamic modeling studies to examine these aspects of estuarine and coastal aquatic science. Jeremy holds a PhD in biological oceanography from the University of Maryland and a BS from the SUNY College of Environmental Science and Forestry. And so with that, I'm going to move you all back. And I'm going to stop sharing and give the controls over to Kate.
Perfect. Thank you, Cindy. Great. So thank you for that introduction, Cindy, and thank you for the opportunity to be talking to you all today on this rainy Tuesday we're having. So as Cindy mentioned, my name is Kate McClure, and I work for the University of Maryland Sea Grant Extension Program as the coastal climate specialist. And I usually like to say that my job is to try to assist coastal communities throughout the state of Maryland with understanding and preparing for the effects of climate change. And so today I'm going to be sharing some examples of how I and my colleagues approach that. But first, I wanted to start with a little bit of an overview of some of the climate-related challenges that our coastal communities are facing. So I want to talk about three kind of major climate-related stressors we're facing here in Maryland: sea level rise, precipitation events, and coastal storms. So starting with sea level rise, we've seen a trend of increasing sea levels for decades. And so this graph that you're looking at right now is based on data from the Solomon's Island tide gauge. And you'll notice there's this upward trend of sea levels dating all the way back to when they first started recording in 1940. And so according to the data from this tide gauge, the sea level is rising a little less than 4 millimeters each year. And this is happening for a few reasons. First off, sea level is rising all around the globe because of the Earth's increasing temperatures. That's causing ice that's currently to melt into the ocean, which causes the amount of ocean water to increase. And also, as the Earth's temperature increases, a lot of that heat is absorbed by the ocean. And that causes the ocean water to actually expand just a little bit, enough that it is making the volume of water in the ocean basins greater. And that causes the sea level that we see to rise. But here in Maryland and throughout actually the mid-Atlantic region, we're seeing rates of sea level rise that are even above the global average. And that's happening because of a few additional factors. First off, there are potentially some climate-related changes to ocean circulation patterns that are allowing more water to come to where we are on the coast. And also, in particular, we're having some land subsidence here. So in addition to the level of the ocean rising, the land that we're standing on is sinking a little bit. So what we perceive as is happening faster. And that's happening because of during the last glacial ice age, there was a giant glacier pushing down on the Earth's continent, coming down through about New York. It was pushing down on New England, but where we are here in the mid-Atlantic was not under the glacier. And so as the glacier pushed down on the continent where we were was pushed up. And now that glacier has melted, the land that we're on, it's all kind of like returning to where it was prior to that. So we're actually very slowly sinking as well. So when we talk about sea level rise, it's really a combination of both these global and local factors all contributing to it. And because of those climate-related global factors, the amount of sea level rise that we're experiencing is expected to actually increase in the future. However, we're already seeing the impacts of sea level rise here in Maryland. One way that we're seeing that is by increased frequency and severity of nuisance or sunny day tidal flooding. So this is a sort of flooding that we see sometimes just because of exceptionally high tides, not because there was a particular storm event causing rain. And so this is a picture from, I believe it's in Oxford. You can see that there's water on the road, which could potentially impede transportation and infrastructure. In addition, because of sea level rise, there's also saltwater intruding into agricultural fields in some low-lying areas of the eastern shore. And we're also seeing a loss of some coastal habitats, including salt marshes and coastal forests. And so I just want to stress that these are things that are happening, although they are expected to continue and worsen in the future. So in addition to sea level rise, we're also seeing a trend in our region of more intense precipitation events, that they're happening more often and that they're becoming even more intense. And this is happening largely because when the ocean water is warmer, that allows more moisture to evaporate up into the atmosphere, which is then able to become precipitation over the land. And so these really extreme precipitation events that I'm sure you all as Marylanders, have experienced and are familiar with, but they can be really, really problematic in the flooding that they cause, which can be a safety hazard for humans and property. It can damage infrastructure, crops, property. And it can also even be detrimental for water quality because these really extreme precipitation events can create more stormwater runoff that then carries pollutants into water bodies. And finally, the last climate-related stressor I wanted to mention is coastal storms, so hurricanes and nor'easters, because these are the sorts of events that can cause really devastating flooding because of the storm surge created by the storm pushing large amounts of water onto the land. And so these two photos are both of some of the aftermath of Hurricane Isabel in 2003. You can see that's some flooding in Annapolis and also damage to a bridge, I believe, on Hooper's Island or Hoopersville on the eastern shore. So luckily, we don't experience storms of this magnitude in Maryland very often, but the thing to keep in mind is that the impacts of large storms like this are likely going to be worsened by climate change because higher sea levels can cause more coastal flooding, and also more intense precipitation events can mean more flooding because of the rainfall. And so I wanted to share, here are two maps showing that are modeling the storm surge inundation from, it's modeled as basically after hurricane, and it's showing what sort of inundation or flooding from the storm surge was likely to have occurred in 2003 and what it's projected to be like in 2050. And so the takeaway from these images, I just would like you to notice that even just like over the span of a few decades, that's about 50 years, we're still expecting to see the area that's flooding to increase and also the depth of that flooding. So even like the same sort of storm back then will have even greater impacts in the future. So that's kind of an overview of what some of these climate-related challenges look like. And I wanted to talk a little bit, so for the rest of my presentation, on how some of the ways that Maryland Sea Grant is working to address these issues in Maryland. And so Sea Grant is it's a federal university partnership between NOAA and 34 university-based programs. There are programs serving every coastal and Great Lakes state. And the goal of the program is really to serve as an unbiased, honest broker of scientific information. So here, the mission of the Sea Grant program is to really serve as a bridge between scientific expertise and the needs of people who manage, conserve, enjoy, and make their living from the Chesapeake Bay and Maryland's coastal waters. And Sea Grant works towards this mission by funding research, by running a few educational programs, conducting education and outreach and communication projects, and then also through extension work. And so the role of extension is really trying to connect industries, decision makers on the coast to resources and science-based information from universities and federal agencies and other sources, so that those people on the coast can make really well-informed decisions and then take action based. And so this can look lots of different ways depending on the context and the needs of a particular audience. But kind of two themes of our coastal climate extension program that I'll be focusing on today are, one, working to build connections and facilitate partnerships, and then also working to translate that science-based information for specific user groups. So one audience I wanted to start off by talking a little bit about that we focus on quite a bit is local governments. And that's because here in Maryland, a lot of the decisions that a lot of the decisions are being made at this local government level, either by municipalities or counties, that are shaping how communities are able to adapt to these climate-related changes. So it's the local government level is where a lot of the zoning and land use decisions are made. They're deciding how to manage floodplains, doing long-term planning, how to restore shorelines, mitigate flooding, all sorts of different planning and project activities. And so this is one place that one user group we really focus on with our coastal climate resilience efforts. So one strategy that's been really effective in Maryland is thinking about regional partnerships for these local governments. An example of that is this Eastern Shore Climate Adaptation Partnership, which is coordinated by the Eastern Shoreline Conservancy, but Sea Grant has been a partner of since its beginning. And the real benefit of this partnership, it has all of these counties and municipalities coming together, working towards climate adaptation. They're able to pool their resources and achieve more than they might be able to as an individual jurisdiction. And continuing on with this local government theme, an example of how we work to translate science-based information for a user group like this is so every 5 years, the state of Maryland produces sea level rise projections. And back in 2018, we had the newest report with projections, and it includes it's called probabilistic projections. So instead of having just one sea level rise value for a time point in the future, there's a range of estimates, each with an associated probability. So this is really fantastic because it's a lot more information you can use in planning decisions, but it's more challenging and complicated to know what numbers to actually use. So we're working on a project right now with the Department of Natural Resources to try to translate some of the content of this report into more of a step-by-step guidance to try to make it easier for these local governments to incorporate the best available science into their planning. And so in addition to local governments, another audience that we work with a lot are coastal residents, so more at the actual community level, people who are living on the coast being impacted by these issues, by either their homes or their properties might be flooding, or it's affecting their commute or ability to get to school. And once again, back to that theme of partnerships, one way of approaching this, there's been a project, this is also from the Eastern Shore, the Deal Island Peninsula Partnership, which started back in about 2013. It started as part of a research project led by anthropologists from the University of Maryland. But since then, it's developed into an ongoing partnership between the university and the Department of Natural Resources and community members, all working together to try to increase the resilience of their local environments and communities to flooding. And this has been an interesting example of how sometimes it can be really important to try to facilitate the connections between residents, county government, state government, and also pulling in other partners. And this has resulted in them being able to do some shoreline restoration projects that they probably wouldn't have been able to otherwise. And finally, one last example with coastal in terms of, back to that theme of translating information for specific user groups. This is a project I want to share because it's something new and I'm excited about. We've been working on putting together a guide for people who are considering purchasing property in coastal areas, to help them better understand some of the hazards and regulations unique to that area that they might want to be aware of before investing in a property. And so this is, it is still in its final editing stage, but it should be coming probably early 2021 or so. So please keep a lookout for that as well. So these are just a few examples of some of the ways we're trying to chip away at this really huge problem of climate change impacting coastal communities. I'll leave it there, but I'd be happy to talk more about anything I mentioned during the Q&A or my contact information if you'd like to follow up later. And that's the Maryland Sea Grant website, which also has some more information about some of these projects. Thank you.
Awesome. Thank you so much, Kate. I'm going to transition over to Jeremy now. And And I will remind folks that the chat box is open through this whole thing. And so as questions pop into your mind that you would like us to discuss during the Q&A portion, please feel free to just type those right into the chat when they pop into your head. No need to hold them. And we'll go through them as they come in. So thank you for that. And Jeremy, it's on you now. Thank you.
Can you see my presentation?
I sure can. It looks great. Thank you.
Great. Well, thank you for having me here, and hopefully I can communicate some basic information about the types of changes that have happened in the Patuxent Estuary, which is where I'll focus, that are related to climate. And although I'll show a fair amount of data in this presentation, I guess the idea was to try to summarize the major changes that we are pretty confident in, and then at least speak at the end about what some of the potential consequences are for those changes in the estuary. I want to start with this drawing of Heracles kind of fighting this multi-headed serpent. Use it as a sort of analogy for, the challenge with managing coastal systems under climate changes. There are so many different factors that we associate with climate change, like temperature, changes in carbon dioxide, sea level rise, precipitation, changes in winds, changes in cloudiness. And it's almost like once you understand one of those things, two more pop up and present new challenges for us to understand. And so like Heracles, who would cut off the head of one of these serpents only to have two spring up from where once was, it's relevant for the way we think about these coastal systems. And, I think a lot about things like dissolved oxygen and algae in the water, kind of traditionally what we associate with the process of eutrophication. And so how this nutrient loading that tends to degrade coastal ecosystems interacts with these changes in climate that we pursue, or that we understand to happen. And I gave a presentation at an international eutrophication conference in Denmark a couple years ago, and I surveyed the participants in that meeting and asked them a bunch of questions about eutrophication. And when I asked them this question, or asked them to react to the statement that we sufficiently understand the interactions of eutrophication and climate change, 70% of the participants either disagreed or strongly disagreed. And then at least another 10 or 15% were undecided. So it's just reinforces this idea that we in this community that tries to understand how estuaries are changing in the future still are fairly uncertain with what these outcomes will be. I also just want to emphasize that climate change can both directly and indirectly influence estuarine systems. And the indirect effects are how changes in the physical environment kind of cascade through this coupled human natural system that we all live in. So just to sort of simply lay that out, if you consider that we have like a policy and regulation in place to reduce the amount of nutrient and sediment that comes into Chesapeake tidal waters and the Patuxent in particular, that those policies and regulations, they either encourage or mandate restoration, but they also may lead to changes in economic decisions. Those can interact with the watershed and watershed processes, leading to an input of some material to the tidal water. And then there's a response in the estuary to that. I mean, this is sort of how our management of the system interacts with the physical environment. But climate change, broadly can affect, the how good the restoration activities are in achieving their goals. It can affect economic decisions. Let's say farmers start planting crops earlier because it's warmer. Climate influences watershed processes by changing, how fast certain things happen in the watershed, and therefore how much nutrient might leak out of the watershed. Climate change is obviously going to impact policy and regulation because, even right now as we speak in the Chesapeake Bay program, there's a big effort to try to understand what climate changes will bring to the estuary and how that influences how the system's managed. And of course, there's a direct response, just warmer water, more precipitation, all of those things will affect the estuary. So it's this complex web of interactions that I can't possibly speak to today, but I'll try to give a few examples of what I think are at least some of the features of this that we understand the best. So to give an example of some of this, I'll start by showing you a time series of the nitrogen inputs to the Patuxent River measured in buoy. And this was put together by my colleague Walter Boynton and one of his students, Jim Hagee. And so you're just looking at the loads over time from 1960 to about 10 or 15 years ago. And if you follow this over time, you can see that the loads were low in the early part of the record. Often that's associated with having low nutrient inputs on the landscape, but it was also a pretty prolonged drought in that decade. And then as the 1970s, which were a relatively wet decade, combined with elevated nutrient loads coming from what we do on the landscape, there was this increase in loads. And then some management actions were taken, particularly to reduce the amount of wastewater nutrients coming into the system. And so you can sort of see a downward path in the inputs, but it's all kind of moderated by what the local climate's doing. So we had this drought period in the around 2000 and low loads, and then we had this really wet year in 2003, and there was just a lot of load coming into the system. So the physical environment just has a really strong, almost overwhelming effect, on how much water comes into the estuary and therefore how many nutrients enter the estuary. Now, one of the main reasons it's of interest to try to understand how these climate effects might impact the system is that the Patuxent, as a clear example, when you look at the various health metrics that are quantified for the different parts of the Chesapeake region, the Patuxent's health is kind of stable, perhaps declining ever so slightly, but it certainly tends to score lower than the overall Chesapeake Bay and even some of the tributaries. So there's a need to sort of understand to what extent does this kind of, if you want to call it stable, kind of poor health for the Patuxent, what might be causing that and how might climate change be a factor? Okay. So this might be something that many of you know, but I'll just try to say it in short. And I just want to highlight, three kind of major features of climate change that will impact estuaries and what that might mean. So we know, and we saw in the last presentation, that there's changes in precipitation and presumably river discharge that we're expecting to see in the future. And so that will alter, as I showed before, how much nutrient comes into the system. It changes how the layering of the water occurs. That would maybe lead to less oxygen replenishment in deep water, leading to more low oxygen zones. Maybe the inputs are more flashy if there's these, more severe precipitation events. And in a lot of the small streams in the watershed, these really big events can be much of the nutrient input that comes in from a particular piece of the watershed in a given year. Warming is also a feature that I think everyone's quite familiar with, and it can just have so many different impacts on the system, especially in the temperate part of the world that the Chesapeake and the Patuxent are in. You have these big annual temperature cycles, and when you start changing those, the ecosystem's kind of cued into it. And so, the water can hold less oxygen when it's warm, and so it makes the oxygen zones, makes the system more vulnerable to that. The rates of nutrient processing change. The habitat that many organisms are kind of adapted to is impacted. And then sea level rise, which I won't really talk about, but it can also have a number of impacts on tidal waters. And it interacts with warming and precipitation, it turns out. So I just want to go through a few data sets for those of you who may not have seen them, just to show how some climate has been changing and the records that we have. So this is a figure that was originally put together by Carrie St. Laurent, and it records precipitation in two kind of regions of the Chesapeake watershed over the last, say, 100 years. And although you can see that there's a lot of variability in this, both of these lines kind of suggest, certainly in the past half a century, that there does seem to be a slight increase in kind of the moving average in precipitation. And so this is just one way that we can look at to kind of document that there is some evidence of elevated precipitation. And the climate projections for this region also suggest elevated precipitation more often than not. And oftentimes that precipitation tends to be, the predicted elevated precipitation tends to be suggested to occur in the winter spring months. Another way that we can think about how something like precipitation might impact the Patuxent is just to look at the records we have of how much fresh water enters the system. And so there's a long-term, going back to the late 70s, river gauge at Bowie, right where Route 50 crosses over the Patuxent. And what I'm plotting here is just the annual mean flow that's measured at that station from 2019 back to 1978. And so you can see that there's a lot of wiggle in that data, and you might even convince yourself that there's been a tendency for slightly more higher flows in the recent year, but it seems more or less flat. But if we look at the summer river flow coming out of Bowie, between the months of June and August, there's a small but significant increasing trend in that discharge. And so this at least suggests that there's the potential that, as we try to reduce nutrients in the watershed, we're kind of running uphill against, periods of time at least where there's elevated discharge, which will continue to add nutrients to the system, even though we've managed to cut off some of the sources. Water temperature is another big aspect of climate change that there's a growing number of evidence for in the watershed itself. So here's just a couple examples for those of you who haven't seen them. The panel here on the left is the annual water temperature, the mean, going back to 1938 from the pier at the Chesapeake Biological Laboratory. It's one of the longest records we have in the region that's actually measuring the water. And you can see that, since the 40s and 50s, that the annual temperature has gone up at least 1.5 degrees Celsius. So it's a pretty substantial increase. And over the same time period, this is just another measure. It's kind of adding up the warm days, accumulating them in a year. And you can see that, this accumulation of warmth is one way to look at this. Its increase has perhaps been more dramatic and more linear, than just the average temperature. So even looking in our more recent data sets that are a little bit more spatially resolved, there's evidence of this temperature increase. So on the left here is an analysis of remote sensing data for the Chesapeake done by some of our UMC's colleagues. And the colors here, the redder they are, the warmer they are, indicate elevated rates of warming. And so if you look at the Patuxent, you can see that in the lower and middle part of the Patuxent, this rate of warming is on the order of 0.1 degree per year, which over this record, which is about at least a little over 25 years, right, means that that would suggest a warming in the ballpark of 2 degrees Celsius in some of these waters. And so that's pretty dramatic. If you look at the Bay's monitoring data and the Chesapeake Bay program's work to look at trends there, these up arrows are significant increases in temperature, and these would suggest a slightly less rapid increase in temperature, so more in the order of 0.75 over the degrees Celsius over the whole record. But regardless, there's warming that's happening. Okay, so I want to spend my next and last few slides just trying to give some examples of how some of these changes might impact the river and how it might depend, the response might depend on where you are in the river. So this is a figure that was elaborated on in more recent papers, but what it shows you on the y-axis here is the algal biomass that we measure with chlorophyll, and against some metric of input to the system. So for the upper estuary, it's river flow. For the middle part of the Patuxent, it's total nitrogen load. And what is really most important here is if you look in that upper part of the estuary, the more flow you have, and this would mean more nutrients as well, but also more sediments, the lower the phytoplankton biomass or chlorophyll you have, right? And so if you compare that with the middle estuary, you see kind of the opposite signal. So the more nitrogen load, which is really highly related to the flow, the more algae you get, right? So if you think about how flow and precipitation might change in the future, it might actually reduce one of the target metrics that we use to evaluate health in the upper reaches, but actually enhance it in the lower reaches because there's enough light there and the algae just take advantage of the nutrients. And so, one of the reasons why river flow reduces algae is because either it makes the water more turbid and so they don't have as much light, or it just flushes them out before they can really accumulate. And so, at the Jug Bay Nair, there's these really high resolution data there that are really kind of telling. And, they measure aspects of the water every 15 minutes, and they measure chlorophyll, one of the water quality targets that we often think about, and also oxygen, which is the second panel here. And this is over the period from May to November, these data. And I think I can't remember what year it was, but it was in the sort of early to mid 2000s. But I just wanted to point out what you can see here and how it might relate to climate change. So on the bottom panel here is the freshwater input. So you can see during June and early July, there's this period of really low flow. The turbidity is really low, and the chlorophyll and oxygen is really high. So the algae are growing really fast. They're producing all this oxygen. The waters are, even though they're high chlorophyll, the oxygen levels are really good. And you can see another period like that after a really low flow period, right? So there's not all this flow pushing the algae out of the upper part of the Patuxent, but they're actually accumulating, and you see the oxygen accumulate as well. But the minute you get a big flow event here, you can see that that bloom crashes, the oxygen drops down to pretty low levels, and you see all this turbidity. And you can see that happen in July as well, where you get a couple of big rain events. The oxygen really goes down, the chlorophyll is low. And so you can see how, not only does the flow affect oxygen or chlorophyll up here, it also affects oxygen in a way that typically makes it lower and dropping below many of the thresholds that are managed for. So just to finish this note, one thing we've been doing recently is looking at these types of high frequency oxygen records in the Patuxent and trying to understand what factors that we have measurements of really influence whether or not we have oxygen below certain metrics. So what I'm showing you here is that record from Jug Bay, and the line is at 5 milligrams per liter, which is one of these metrics. And where we've analyzed what drives these low oxygen concentrations, symbols here represent the variable that's most important. And so throughout most of the Patuxent, the water temperature is the most important driver. And here it would sort of suggest that, because warm conditions, they speed up the rates that remove oxygen from the water, and they just simply prevent the water from holding as much oxygen as it otherwise would. You see the oxygen concentrations decline under those conditions. And similarly, if you just look at the whole Patuxent and how much low oxygen water it has in a year, that's what's expressed in this figure. The more flow you have on this y or x-axis, the bigger you tend to have these volumes, right? So just thinking about what this wetter future will look like will probably also support lower oxygen conditions. So I don't present these data to communicate pessimism, but I just want to communicate kind of our understanding that these aspects of the physical estuary that really respond strongly to climate, they're going to be working against the efforts to restore the system. So this is one of the reasons why our management community is so laser focused right now on trying to understand and quantify what these effects will be. So to conclude, just in short, I can leave these up here, but I just wanted to communicate that these climate changes, they're effective throughout this coupled watershed human society estuarine system, and that we're already seeing the effects of these climate changes. They're already evident even in our recent records. The Patuxent's a complex estuary, and so no one simple set of relationships between climate and the health of the water really are fit, and so we have to think about it along the salinity gradient. It's hard to to deny that a warmer, wetter future was going to put some more pressure on the ability to meet certain water quality targets. And that we can make some reasonable predictions about how physical properties will change, but we really just don't know how the biology will change in the future, how it will adapt, and how resilient it will be. And so I focused on kind of these physical properties today, but there's a whole wealth of information about the biology and how you could imagine it might play out here. So thank you for your time.
Thank you, Jeremy. Thanks, both of you. Those were excellent talks and gave us a lot of things to think about. So I'll remind everyone that please send in your questions for the Q&A via the chat box. And while people are working on that, let me turn on my video so I'm not just a disembodied voice for you all. So while folks are working on their questions and sending them in via the chat, I will start off. And one thing that I think many folks might be interested in hearing your thoughts about is what could people do in the Patuxent watershed or elsewhere to help promote these healthy ecosystems? So it's mainly directed at Jeremy, just thinking about your final slide about the climate change, of course, is here and is affecting our river. But what could we do as people living in the watershed to help promote a healthy ecosystem in the face of all of that? Do you have any thoughts about that?
I feel like I should have a really clear answer to this question because it's one that I kind of get asked a lot. For anyone that sort of owns property, there's always an opportunity for you to sort of think about, what you put, on your lawn and on your property and how you kind of manage water on your property, because anything you can do to, reduce your own nutrient footprint will sort of help our kind of best buffer against the climate change, which is probably to reduce nutrient inputs. So, managing your septic system and anything like that. Another thing I'd just like to raise while I'm thinking about this is there's a movement in some of the community that I work with that has, is starting to think beyond restoring the watershed and start thinking, well, how can we achieve restoration goals by doing things in the estuarine waters themselves? Are there nutrient removal efforts that we can put in the water? And so it sounds more like an engineered situation, but it's, thinking beyond the restoration having to happen in the watershed, and that maybe there's things you can do in the tidal water. So just, assigning nitrogen removal credits to oyster aquaculture is kind of the first step in that kind of thinking. Let's stop.
Hey, Jeremy, I have a question for you. So when you show that map about the temperature changes on the water on the Chesapeake Bay, so I mean there are differences in the different water bodies. What do you think is driving a little bit the higher temperatures on the Patuxent River? Is it depth, or if there's anything else?
That's something that I wish I had a better answer to. One of the things you can see in that record is, there is a little bit more of a warming that you see kind of in the urban areas and, somewhat closer to shore. Then if you look at that map, if you remember it, there's also a bit of a warm blob around the Calvert Cliffs nuclear power plant. So you can see a little bit of that there. In terms of this part of the lower Patuxent, I've been starting to think a bit more about the residence time of the Patuxent and how that plays into its response to a lot of things that have changed over time. And although, the estimates that we have put it at somewhere between sort of 60 to 80 days, which is a fairly long time, and it's, residence time, what I mean is sort of like how long, a given parcel of water that enters the system sort of stays there before it's flushed out. So the longer the water, has to stay around there, it's possible that its potential to warm, especially if you consider that the main stem Chesapeake is probably a little cooler, that might be one of the reasons that's the case. But other than that, that's a speculation. I don't know that I have a clearer answer than that.
Thank you. a little bit to follow up. I mean, I know you didn't really bring up the salinity intrusion, but I know it can be maybe a big deal on the Patuxent River. Do you have anything to say about that? I mean, I know like the upper and the middle and the lower Patuxent have different characteristics, but do you see how maybe a salinity intrusion changes actually can impact the Patuxent overall?
I think it's a little bit out of my range of expertise, I think, to consider how that might affect the system. You know, I start thinking about the tidal freshwater marshes that kind of blanket, you know, the upper part of the tidal river. But I don't really have a good handle on how vulnerable they are to this. But one thing that we've noticed looking at the Patuxent data is in some of the really upper parts of the river, there are pretty clear increases in conductivity over this record that we have that goes back to the mid-80s. And my recollection of those is that they're even in some of the non-tidally influenced streams, which sort of indicates that there might be, you know, like a road salt type of signal there or something else that's increasing the conductivity. But it would sort of suggest that there's, you know, that kind of stress could be coming not only from sea level rise, but also from the upstream.
Great, thank you. Hey, Kate, quick one for you. So, I mean, you were talking one of your last slides about some of the tools that, you know, you guys are developing to help the stakeholders. How well received are these kind of tools for people? I mean, I know at the beginning, people were kind of like reluctant to accept, I guess, climate change and everything associated with it. I don't know if you have experienced a good reception. People are becoming more aware of the real impacts and how they use these tools.
Yeah, I mean, it's a little bit of a complex question to answer because I think it varies a lot among different stakeholder groups and specific individuals within them. What I see in my work is that there's a lot of willingness to acknowledge that there are changes in the environment and that those are creating problems. Sometimes the discussion about what to attribute those changes to can be a little bit more fraught, but particularly focusing on adaptation options of ways to address the changes that we can all agree are seen. I think it's perhaps a reason for some optimism that I don't see though. It's not that contentious of a topic typically among most audiences. Of course, there are always exceptions.
Great, thank you.
So following up on that, Kate, could you maybe tell us about some of the biggest challenges that you face in your work surrounding these ideas?
Sure. I mean, I think that one of the challenges doing anything related to climate adaptation is that even though we are seeing these changes already, you know, just like a hypothetical that the sea level is rising and that'll be a problem in the future. Like we're actually seeing the flooding impacts now. But despite that, it's a relatively slow moving problem. And so it's an ongoing challenge of making sure it gets the attention it needs now, particularly in terms of making decisions today that are impacting, you know, where people are living and how we're living, you know, decades in the future. It's challenging when there's other things that feel more urgent and pressing. I mean, this is something that we're seeing right now with the current pandemic. I mean, totally understood. Like, how can you expect local governments or other stakeholders to really like think beyond the current crisis? But like with climate change, it's like we really need to have that continued long-term engagement on the topic.
Yeah, thanks. And I'm going to throw the same question to Jeremy about what are the challenges that you face in your work that may be a little bit different, thinking about the scientific aspects of it and also engaging with other folks as well. What are some of your challenges?
I mean, from I guess I have like maybe there's a three-part question. The first is, one challenge is, we have is finding the information in the records that we have to really understand, or to kind of quantify and directly associate particular changes say, something related to climate change like temperature, and how that relates to some other information that we have that we're interested in, like, how much flow oxygen is there. And so I think scientifically we're always sort of at a data challenge. Do we have enough information to really definitively link something to another? From using the information that we know to support management, I think when we're trying to communicate that information and use it to make projections, we often find ourselves using models to do that. And although, if you're interested in something like oxygen, to use the same example, you can, I guess, make pretty good estimates of what oxygen conditions are supposed to be like, or might be like in 30 years, because it tends to be primarily driven by physical and kind of microbial processes that we have a pretty good handle on. But once we start thinking about how that will impact organisms, or how the communities of organisms that live in this region might change, just because species adapted to different conditions might just take over. Some species will go, others will come. Maybe the ones that come are more resilient than the ones that went. And so it becomes, this biological response uncertainty, I think, becomes something that's a bit of a challenge. And finally, with, I guess, my question about, what can, we do as citizens, I think it's hard to identify what, we all can do to mitigate climate change on a very local level. We only have so much control.
Yeah, and so we have had one question come through the chat, and it goes along with what you were just talking about, Jeremy. The question is, are you forecasting when keystone species will begin to fail?
I'm not doing that. And I don't know, in particular, what species we might be most concerned about. I mean, one of probably the more well-documented examples is the eelgrass that is one of the dominant seagrasses in the lower parts of the bay. It's at kind of the southern limit of its habitat down here, and it's pretty vulnerable to temperature extremes. And so as the water's gotten kind of cloudier, the eelgrass has had to sort of rely on its shallowest waters, and those are the ones that are most vulnerable to these heat extremes. And so, that's one of the species that I think people have some concerns about regarding its future in this system.
So we're coming up to the end of our hour, but I wanted us to end on an upward note. So we talked a little bit about challenges. So I was wondering if each of you could highlight one success that you have found that gives you great optimism. The great part being my word, maybe not yours, but at least some optimism of how things are doing in the Patuxent. So we'll start with you, Jeremy, and then we'll go to Kate.
I think one thing that we've seen in the Patuxent is that when the wastewater treatment plant loads to the system went down, even though the lower parts of the system didn't recover that quickly, parts of the system that were more adjacent to where the sewage treatment loads were actually happening did seem to respond in the right direction. And that's type of reaction to big wastewater treatment reductions that's positive has been seen in the Back River and the Upper Potomac and the Upper James. And so I think the optimism there is that when we are successful at reducing nutrient loads substantially, we do tend to have some good examples where, something that we might call a recovery starts to happen.
Sorry, Cindy, could you say the question again real quick?
I probably couldn't if I tried to now. My basic question, we have talked about challenges that I wanted to time together on a somewhat optimistic or hopeful note. And in that vein, I was wondering if you could highlight a success that you've seen in your work.
Yeah. I mean, I appreciate you having this be the note we end. Climate, I think, gets kind of dragged down with all the challenges. I mean, particularly thinking about ways to adapt to these challenges. There's so many opportunities, and because I mean climate is impacting so many things, there's so many ways that we can do things about those. And I mean, I have a lot of optimism about it because in my work, I see people at all levels of government trying to work towards advancing this, and I see residents asking about what they can do. And I think we're kind of at the point where we're starting to move from thinking about what we could or should do into starting to implement some of these things. So yeah, so I think that there are a lot of exciting opportunities in that way. And if I could just end with to back up to some of the things you were talking about, what residents can do as individuals to take actions on these. There are a lot of things individuals can do to reduce their carbon footprint or improve stormwater on their properties. And these are all super fantastic, and everyone should absolutely do those. But one thing I think about a lot is how climate change is a really big problem, which means we need big solutions. And so I just like to encourage people to think about ways they can be part of those larger solutions in their communities whenever possible, whether it's by voting this week or next, or all of these plans that your local and state government are putting together to kind of make roadmaps of how they're going to address these problems. They all have opportunities for public input, and those can be really powerful ways that residents can help guide the direction that we're going with this. So thank you.
Thanks to both of you. And I think that brings us to the end of our time together today. So I definitely want to thank the two of you very much for all of the time you put into your presentations and for being with us today. I'd also like to thank our steering committee. I have a slide that I'm going to share with everyone. Yeah, I think that's the right one. Okay. It's always dangerous, right? When you go to share your screen, that moment of like, what am I showing? So I'll leave everyone on this slide right here. This acknowledges our partners and our sponsors. And importantly, if anyone has any feedback on the presentation and also on any of the WebEx details, we have a few more sessions coming up, so we could definitely carry that feedback forward through our next sessions. So please send it to that email address right there. And please remember to register for the following seminars in our series. The next one is next week on the 5th, and we hope to see you all there. So thank you very much, Jeremy and Kate. And that's a wrap from my end.
Thanks, everyone.
Thank you.